Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Greetings to grade 10s. Welcome to the session tonight. Okay, we want to finish up the paper 1 that we did last week. We just had question 2, 3, and 9, as well as question 1 to do. And then we'll move on to during revision for paper 2. Okay, so let's do question 2. It says a boy walks in an easterly direction, as shown below. He passes a tree and continues in the same direction for another 20 meters. He then stops, climbs on his skateboard, and rides in a westerly direction for 25 meters before he finally stops. The resultant displacement of the boy when he finally stops is 10 meters east of his initial position. 2.1. Define the term distance. Okay, we'll let everybody answer in their own time, just after we've gone through all the questions. 2.2. Determine the initial position of the boy relative to the tree. Calculate the total distance that the boy moved. And when the boy is on the skateboard, he skates at an average speed of 5 meters per second. Calculate how long in seconds the boy is on his skateboard before or during the motion. And 2.5, the total time for the motion of the boy from his initial position until he finally stops is 40 seconds. Calculate his average velocity. Now, one thing worth mentioning about this question is that they have included quite a bit of mechanics in the first question 2, which is usually not as asked. Okay, so we've got a bit more calculation questions in terms of velocity here. We've got some time questions here as well, 2.4 and 2.5, making question 2 a little bit slightly more in terms of marks. Okay, so this is still displacement, this is still frame of reference, or this is still the vector question, okay, of the paper, just asked a little bit more with reference to actually calculating values, etc., etc. We know it's the vector question because we're given a compass direction here as well. Okay, so let's go for these answers. I think I just need to give you that line. All right, and we all should be fine, and then we'll mark in about 12 minutes. First question was define the term distance. All right. Why do I have 2 of these? Oh, there we go. I don't know why I had more than one board open. Anyway, now it's a 2-mark question, not a lot of writing that's needed. Okay, so that means we just need to write that it is the total path traveled. Or we can say, maybe to be more specific, total path length traveled. Or if you say total path traveled, all right, should get the mark as well. Okay. The next question: determine the initial position of the boy relative to the tree. Okay, so let's see. He goes easterly as shown below. He continues in the same direction for 20 meters, and then he stops, climbs on his skateboard westerly for another 25, so he covers the same 20 meters plus an extra 5. The resultant displacement of the boy when he finally stops is 10 meters east of his initial position. Alright, so that means he stops before that position there. And they're asked to determine the initial position of the boy relative to the tree. So the relative to the tree, so that position would be the original position. Okay, will equal to the 10 meters, that's his resultant from his initial position, plus the extra 5 meters that he travels in the westerly direction. And that will give us 15 meters west of tree. I hope that makes sense. Any questions? You're welcome to ask. 2.3, calculate the total distance that the boy moved. Okay, So we got this 15 meters here, so we can just call it distance, or total distance should equal to the 20 meters plus the 25 meters plus the 15 meters, and then that'll be 60 meters in total. And then 2.4 requires another long list of calculations, so we're going to have to move over to the next layer here. Okay, 2.4 was when the boy is on the skateboard, he skates an average of 5 meters per second. Calculate how long in seconds the boy is on the skateboard during the motion. Okay, that is V is equal to delta X over delta T. Okay, the standard velocity formula, and then that should equal, well, the velocity we know is 5 meters per second. The delta X, the displacement is 25 meters, and we're looking for time, so that's going to equal 25 divided by 5. Therefore, the time is 5 seconds. Okay. 2.5, the question was the total time for the motion of the boy from his initial position until he finally stops is 40 seconds. Calculate his average velocity. Okay, well, his average velocity is the same formula, delta X over delta T. So we know that the displacement resultant was 10 meters, as the little paragraph before the question told us, and it said it was 40 seconds till stoppage. So therefore, average velocity is equal to 10 divided by 40, which is 0.25 meters per second. It's positive, so its average velocity is also in the easterly direction. And 0.25 meters per second east is the final answer there to that question. Okay, and that was 12 marks, ladies and gentlemen. Nice and simple. Okay, let's move straight on to what happened there, to question 3. Okay, this is also more of your mechanics question, still a mechanics question. An airplane touches down on a runway at a velocity of 67 meters per second as illustrated. After 30 seconds, the velocity of the airplane is 8 meters per second. The airplane then continues at a constant velocity for a further 800 meters before leaving the runway. The length of the runway is 2,000 meters. Alright, 3.1, define the term vector. Okay, well, we all know this, so maybe I don't need to write it down, but you know, let's just write it down anyway. Let's just get rid of these two blackboards because, or whiteboards, because we don't need them. Alright, question 3. Alright, so a vector is, first of all, a physical quantity. The first part of this definition, it's a physical quantity. And with magnitude and direction. Okay, don't write this little and symbol here that you see on your keyboard that's above the number 7. Okay, don't do that in your exam. Rather write A and D. I'm just lazy at the moment. Okay. Right, they ask us to convert 67 meters per second to kilometers per hour. Okay, that's a very easy conversion. I'm sure we all know or remember how to do that. We just take 67 meters per second, multiply that by 1 over 3,6. Oh, excuse me, I'm talking complete bully. That's to get kilometers per hour to meters per second. If you want obviously to go from meter per second to kilometers per hour, we just have to multiply it by 3,6, and we'll get 241,2 kilometers per hour. Alright, to convert meters per second to kilometers per hour. Okay, now 3.3, it starts to get a little juicy. Oh, sorry. From 3.3 starts to get nice and juicy there. Let's just leave this little piece up here. I think, yeah, 3.3.4 is the last question. 3.3.1, calculate the acceleration of the airplane during the first 30 seconds. Now, this is an equation of motion question. 3.3.1. Okay, so now we're going to use what we know. First of all, we know that the airplane touches down at a velocity of 67. So we know that VI is equal to 67 meters per second. We know that after 30 seconds, the velocity of the airplane is 8 meters per second. So VF is 8 meters per second. We know the time there is equal to 30 seconds. Okay, and we want to find out the acceleration of the airplane. So we're going to use a formula. I'm going to use a different color for this one. VF is equal to VI plus A times delta T. So we've got 8 is equal to 67 plus A times 30. Okay, which is going to end up being 30A. Okay, now we are going to get a negative answer here because we've got 8 minus 67. We should be, I think, 59. No, not 59. Am I right? Yes, I am. 59. So minus 59 rather is equal to 30A. And then we're going to divide both sides by 30. And we'll get acceleration is equal to negative 1,1966. So that's 1,97 meters per second squared. And to finally end off our answer, we'll say, therefore, acceleration is equal to 1,97 meters per second squared. And we end off with given a direction because it's a vector. So we'll say in opposite direction. Now you can write it like this in your exam, in op direction. They should get the mark as well. Okay. However, for exam purposes, because you don't know, because obviously everything you do now in your FET phase, which is grade 10, 11, and 12, is preparation for grade 12. And a complete stranger marks your matric final paper, so you just want to make sure that, you know, write everything in full, so that they can, everything is clear and outlined for them, so they can give you the marks that you need. Because obviously everything in grade 12 is valuable. Right, grade 3.3.2, the distance that is traveled by the airplane during the first 30 seconds. Okay, so we're going to need another layer for this. Let's go all the way to the top here. Here we go, 3.3.2. Okay, so let's see, what do we know? Okay, there's three possible answers for this. I'm going to use the formula VF squared is equal to VI squared plus 2A delta X. Reason being is because I have final velocity, I have initial, and I have the acceleration that I just calculated, and I could just find delta X. Or I can actually use the delta X formula, which is this formula. So I'll put a slash here. Delta X is equal to VI times delta T, because we also have time, it's 30 seconds, plus a half A delta T squared. You know what I'm going to do? I think I'm going to, so you can choose whichever one you want to. I think I'll rather do both for this one, but we will get a slightly different answer, I think, for either one. Okay, so I'll rather just extend it through the entire page and work with both. Right, cool. Let's do the left hand side first. So VF squared, we've got 8 squared is going to equal to 67 all squared plus 2 times negative 1,97. Remember, not just 1,97. We got a negative answer, delta X. Right, so that's 64. And I'm going to take this over, and that's minus 67 squared is 4,489. That's going to equal to, rather, negative 1,97 times 2, that is minus 3,94 delta X. Okay, so 64 minus 4,489, that's going to give us minus 4,425 is going to equal minus 3,94 delta x. Then divide both sides by 3,94 or negative 3,94, and therefore delta x here will give us an answer of 1,123,096. So let's make that 10 meters. Okay, pretty accurate answer. Okay, we might get a different answer with this one though, because with the second formula, doesn't matter because we're still using the correct numbers. Okay, so delta x is going to equal VI, which was 67 times 30, plus half of the acceleration, which is minus 1,97 times 30 squared. Okay, so that looks like that's a straight enter on the calculator, and then we should get an answer for delta x. Okay, so let's do that. 67 times 30 on the 1 plus half of minus 1,97 and times that by 30 all squared. Right, let's see. We get 1,123. Our decimal is just different. Our decimal is 0.5 meters. Right, so go 0.50 meters. Okay, so that was question 3.3.2. Either answer they would have given you as the correct answer anyway, so nothing that we needed to stress about there. That's the same place I found the exam. 3.3.3, the time taken by the airplane to travel the 800 meters. Okay, so this happens between the first 30 seconds, and then there's 800 meters that is obviously unaccounted for, which is obviously the rest of the runway, because the length of the runway is 2,000 meters. Okay, cool. And it doesn't look like this arrow extends to the end here, so it's probably 800 meter mark is probably somewhere around here. That's the point. Cool. So they want the time taken for that. So we still got space here. So let's maybe just rule a line underneath this one, so we can still use this half. And rule a line here, so we can still use that half as well. Okay, so let's try 3.3.3 here. Okay, let's see. So we want the time taken, so we know that delta x is equal 800 meters. We also know VF is still 8 meters per second. Oh no, sorry, for that last 800, that's going to be VI is equal to 800, 8 meters per second, sorry. And yeah, that's all we need. And let's see, something else I'm missing in the question. Airplane then continues at a constant velocity for the further 800 meters, so we know acceleration is equal to 0 meters per second squared. Let's see, and time is what we are looking for, so delta t is what we are looking for. Okay, let me see if I can use a formula here. Okay. Right, let's use this formula. Let's come down here maybe, or let's use a different color because there's a lot of orange happening here. Delta x is equal to vi delta t plus half a delta t all squared. So we know acceleration is equal to 0, so you know this part is going to equal 0 immediately. So we're just going to be left with delta x is equal to vi delta t. So delta x is 800, and here we've got 8 times delta t, so we divide both sides by 8, and therefore delta t should be 100 seconds. Alright, that looks like a 5. 100 seconds. Alright, awesome. So 100 seconds to travel that 800 meters, okay, which is about 1 minute and 40 seconds. 3.3.4, the length of the runway that is not used when the airplane leaves the runway. Okay, now this will be dependent on what answer we got for 3.3.2 as well, whether we chose this one, whether we chose this one. I'm going to choose this one. All right, but basically the formula for it is length not used. All right, the length that's not used will equal to the 2000, which is the total length, minus the 800 that it travels for, minus the distance it travels for the first 30 seconds, which was 1123,5, or if you used this answer, it would be slightly different, and therefore I'll shorten it just to length, which equals to about, okay, it's 2000 minus that minus 800 should equal to roughly about 76.5 meters. Okay, now if you use the other answer there, which you also see on the screen, 1123.1, we'll get 76.9. Okay, and if you used another answer, I think there's a third formula that you can use. The delta x is equal to vi plus vf divided by 2 times by time. I think you'll get a more of a whole number answer there. You'll get 75 meters. So the range will be about from about 75 meters to about 76.9 meters. So yeah, there's a bit of a range, I think, for this answer. Okay, depending on which answer you got for 3.3.2 to get this. But there's about just 75, or just over 75 meters of the runway that is not used. Okay, very nice question. All right, this is a very nice question so far. We're not done yet. We still got 3.4 to go. Okay, so this looks like more of a theoretical question. They say pilots should take weather conditions such as wind and rain into account when they calculate landing speed. 3.4.1. How should a pilot adapt the landing speed if the surface of the runway is wet? Choose from increases, decreases, or remains the same. Okay, let's read that question again. How should a pilot adapt the landing speed if the surface of the runway is wet? Let's choose from increase, decrease, or remains the same. What do the people say currently sitting here in this classroom? If the runway is wet, should the pilot increase, decrease, or keep the landing speed constant? What say the children in the class?
I have no clue, but I'm gonna guess. Um, Decrease? I don't know.
Okay, decreases. Okay, we got one decreases. Any other takers? Anybody that agrees? Anybody disagrees?
I think I'm gonna say decreases as well.
Okay, 2 decreases. No takers for increases or remains the same. Well, let's apply logic here. Okay, if you must drive fast on a wet road and your tires are not really cool, right? Then obviously your car is going to take longer to stop because the road is wet, so it's smoother surface, so kind of not as much friction on the road. All right, that's why I always say don't drive fast on a wet road. Right, a lot of accidents happen when it's wet because your stoppage time is a little slower, right? A little longer to stop. So the same way here, if the runway is wet and the pilot is coming into land, he should probably decrease his stoppage time. So 3.4 or decrease his landing speed, slow the speed down when he lands. So 3.4.1 definitely decreases. Okay. 3.4.2. Explain the answer to question 3.4.1 by referring to the stopping distance in relation to landing speed. Okay, this is a bit of a mouthful. Okay, so let's go ahead and take it down for 3.4.2. Okay, so for 3.4.1, we chose decreases. 3.4.2. All right, well, on a wet runway, okay, on a wet runway, like I said, there's less friction. So another way to put that is that the tires have less grip. Okay, the tires have less grip. And to stop within the same distance. Okay, like I said, your stoppage time is going to be longer, so the stoppage distance will be longer as well. To stop within the same stoppage distance, the landing speed should be less. Okay, there we go. Okay, so that explains our answer to decreases. Okay, well done everybody. All right, I think we had one more to do, and that was question 9, and then question 1 is what we have to do next. Okay, so let's just go check question 9 quickly. Okay, this was a nice question, 20 marks, and I'm sure most of us could have scored between 16 to 19 for this one. Okay, so not bad at all. We've already done question 4 last week. Okay, question 9. Short question, so let's go for it. Question 9, 9 marks. Okay. A compass is used to determine the poles of a magnet. The compass is placed on different positions around the magnet as shown below. The dark arrow indicates the north pole of the compass. Okay. So position 1 and position 2. Okay, I always like to read the opening part of the question more than once. So let's have a look at it again. A compass is used to determine the poles of a magnet. The compass is placed at different positions around the magnet as shown below. The dark arrow indicates north pole of the compass. Okay, position 1, there it is, and position 2, there it is. Okay. Definitely looks like X is the north pole. Okay. Because both of it points to X. Alright, the dark part. Looks like X is the north pole of the magnet and Y would be the south pole of the magnet. Or am I wrong? The dark arrow indicates the north pole of the compass and opposite poles attract. Well, tell you what, the question will probably clarify up everything. 9.1, explain the term ferromagnetic materials. Okay? So it's question 9, so I need a new... Alright. New color. Ferromagnetic materials, okay. First of all, they are materials that are strongly attracted by magnets and are easily, right, or easily magnetized. Okay, how much space do we have left on this one? I think we can still fit some 9.2 here. Alright, 9.2. Is X the north pole or the south pole? Well, if the compass, the dark part of the compass arrow is the north pole of the magnet, then that means north would probably be attracted to the south. So I think X is not the north pole, as I said earlier, which is kind of foolish of me. The dark part here is the north pole of the compass, and both position 1 and position 2 point here. So I'm going to go that X is actually the south pole because opposite poles attract. So X is definitely the south pole of the magnet, as the north pole of the magnet is pushing, or is always turning towards the X position. So it must be south. Otherwise, it wouldn't have both pointed Y. Or position 1, it would have pointed the other way. At which position, 1 or 2, will the compass experience the strongest magnetic force? Give a reason for your answer. Okay. I think it's definitely going to be position 1, because look how close the north pole is to the south pole of the magnet. Alright? It's quite close. Whereas position 2 is a little bit further away. So I definitely, its strongest force of attraction is going to be here at position 1. Okay? Let's go here. Let's pick a different layer and let's write down position 1. So question, no, I don't need to write this. It's for 9.3. Okay, I'm going to write down position 1. Okay, and that's because the magnetic field is strongest at the poles of a magnet. Okay, it's right at the south pole, So definitely going to have the strongest magnetic force reading over there. All right. 9.4. What is the direction of a magnetic field? Choose from north to south or south to north. All right. Let's read that again. What is the strongest direction of a magnetic field? Is it north to south or south to north? It is definitely north to south. Okay. 9.5.1. We're almost done with this question. Give one term for each of the following descriptions. The point on the northern hemisphere where the rotation axis of the Earth meets the surface. There's a term for that called the geographic North Pole. Geographic North Pole. Then 9.5.2 was the point where the magnetic field lines of the Earth enter the Earth. Okay, that would be also North Pole, but not geographic, be magnetic north. Magnetic North Pole. Alright, in geography, I don't know if there are any geography students here, but then you will look at north, true north or magnetic north, and as well, so which you'll have normal compass north, and then you'll have magnetic north or true north or something like that, which is a little bit to, I think it's either to the left or a little bit to the right. I haven't done geography in a few years, so I would have to look at a map to obviously see that, but I'm not going to say that it's definitely left or right. It's just slightly off. Alright, 9.6, state one advantage of Earth's magnetosphere for life on Earth. Alright, and one advantage of that is quite intuitive though, is definitely protection from solar winds. A little bit of theory there. Alright, and that was... Alright, so what we've done now is we've done all of section B's questions. The only thing that's left for us to have a look at is question 1, which is our multiple choice. Alright, and I'll teach some multiple choice skills as well. Before we go on, any questions from the class so far? Any questions on... please go ahead and ask me.
No, not.
Cool, thanks Reese. Alright, cool. Right, don't hear any questions, so I think we should be fine. Alright, let's go have a look at question 1. Let's see. Alright, so question 1, okay, your multiple choice will get given these instructions. They're usually 4 answers, and of course you have to choose one. Okay, now multiple choice is the most failed section, most failed exam style, setting style that exists in the world. Alright, it's easier to fail multiple choice than what it is to fail written answer questions like in session B. It's way easier. Okay, because sometimes in multiple choice, more than one answer, if not all the answers, will look right. I wrote a multiple choice exam, and all the answers were A. I'll say that again. All the correct answers was one letter for each of the question. It was a fully scaled multiple choice exam. I was grade 10, term 4. Made it all A. Alright? No, I did not select A for all of them. You know why? Because in my mind, they were all too good to be true. No, it can't be. So I started to doubt myself. Alright? So, when doing multiple choice, there's a technique. Okay? And this is applied at university style already. Okay? This is how I passed my university multiple choice exams as well. Is that when you're given a multiple choice, you must understand that you've got 4 options. Alright? And each option is broken up into a percentage. 25%. So if you're looking at these 4 answers, you have about 25% chance of getting the question right if you want to guess. So what you want to do is you want to narrow down that options to give yourself a slightly more advantage or a greater chance of getting the question right. So the best way to do that is to eliminate the answers that you know and that you can see are definitely wrong. Okay, so if you can take away 2 options from the 4, you've got 2 options left. That means you've got a 50-50 chance, right? Your chances for getting the question right have increased slightly. All right, so with that being said, let's look at the first question. Which one of the following physical quantities is a scalar quantity? Now, what you can do is first, we can take out option A, because weight is basically gravitational force, and we know that force is a vector, so A gets taken out. B was one that we could have seen was definitely wrong because there's a direction there, and direction is a vector with a magnitude, so B is out. C, current of 2 amps, maybe we're not so sure, so we leave that. D, we can see a negative acceleration of 0.4 meters per second. We know acceleration is a vector quantity, so we eliminate D. What are we left with? We're only left with option C. So option C must be correct, because we know current is not a vector. There's no direction for current. We just give it as a magnitude. We just give it as an answer. So for question 1, let's go all the way up top here. 1.1, option is C. Current of 2 amps, that is our scalar quantity. Let's look at 1.2. 3 forces act simultaneously on an object as shown below. Okay? 3 newtons going to the left, 2 newtons going to the right, as well as 5 newtons going to the right, or east and west. Determine the resultant or net force acting on the object. So we do know we've got 7 newtons going to the easterly direction, and we know that 3 newtons going left is negative, so that's going to be 7 minus 3. So we're definitely going to have an answer of 4 newtons, but our answer is positive. Our positive force, 5 and 2, gives us 7, so that's greater than 3. So our answer can't be 10 newtons west. That's wrong. Can't be 10 newtons east. That's also wrong. 4 newtons west. Our answer was positive, so it can't be west. West is going to the left and it's negative. So it must be option D, 4 newtons east. So that's option D. Which was just, how do we get that? 5 plus 2, 7, minus the force going in the opposite direction. So that's 7 minus 3 gives us 4 newtons east. That should be quite intuitive to understand. 1.3, an object accelerates uniformly when the space of a object changes the same amount in equal time intervals. An object accelerates uniformly when the space of the object changes with the same amount in equal time intervals. Okay, well, it cannot be mechanical energy. So I'm going to take out option D. All right? Because nowhere in energy do we read about acceleration and time intervals when we come to energy. Speed is a scalar quantity. We are not really looking at equal time intervals or the word uniformly with speed. So I'm going to rule speed out. Displacement, that's just a change in position and no acceleration. The only time we look at acceleration is with the word velocity. So for 1.3, it must be option A. So let's read that with option A. An object accelerates uniformly when the velocity of the object changes with the same amount in equal time intervals. All right? Remember, acceleration is the change in velocity over the change in time. 1.4, a velocity time graph for the motion of an object is shown below. The object changes direction at which amount of seconds? Okay? Now, we can see that the object increases its velocity to 2 meters per second, And at 1 second, it reaches to 2 meters per second. And then we can see the velocity coming down, and it changes until he comes to a stop here at 2 seconds. After 2 seconds, he definitely increases his velocity from 0 to -2, which in mechanics means that he's just gone the opposite direction. So, at the object changes direction at how many seconds? It cannot be at A, 0.5 second, or a half second, 0.5 seconds, as that is here while his velocity is increasing in the positive direction. Cannot be A. It cannot be B, because B is when you reach his maximum velocity. It cannot be at point D, alright, because he also reaches maximum velocity there. In the change direction, but they ask, when does he change direction? At which time? At what time? And we can see it must be option C, because he must change at 2 seconds, because after 2 seconds he continues accelerating. Alright, so it is definitely 1.4 is option C. 1.5 says that an object is moving at a speed v, or an object moving at speed v has a kinetic energy E. The kinetic energy now changes to a quarter of what it originally was. The speed of the object is now, okay, cool. So this is a calculation question. Okay, this is a calculation question. All right, let's have a look here. Sorry, initially for 1.5, I'm going to have to work this one out. Picture this E here as 1. All right, 1E, so it's 1 whole. That becomes a quarter E. All right, that becomes a quarter E. Okay, and the question was, an object moving at a speed v has a kinetic energy of E. So now we've got a new energy. Okay, the object moving at speed v, the kinetic energy now changes to quarter E. So what is the new speed of the object? Okay, so in order to get a quarter E as our new this is our new energy, okay, we need to find out what is the new V. Okay, well, that's simple. All right, we need to find out what did V go to, which was normal. Okay, so what we can do is we can say, well, a quarter E, I think that is now a half mv squared. All right, so we want to find out what is V. All right, what did V go to? Okay, to get this, to get this answer. Okay, well, I can definitely see that if we must multiply both sides by 2, we'll just get M and V. Okay, I can definitely see that. Okay, because if this was just normal V squared, that will just be 1V, because this is 1V, so that'll just be 1, and we'll get 1E there. So if you have half here, and if you have half mv squared, and we want to get what that answer was, okay, let me just see how we're going to do this. Let's see how we're going to do this. Multiply both sides by 2, just to get it back to that. So let's multiply both sides by 2. Alright. And if we multiply both sides by 2, we'll get 2 over 4e is equal to mv squared, but that is just, that was 1v, then that is just, so 2 over 4. So I'm thinking, no, hold on. Sorry guys, hold on. I'm making a mess of things here. Right. it's way better to do this. Okay, if E here changes to, this is half mv squared. So what happens if we try, what happens if v equaled a half? It went to now a half v. So now we've got a half, that's going to say a half times m, and let's put in a half v all squared. Okay, so a half v all squared, that's going to equal to half m, and we know that a half squared, let's just put it in our calculator, a half squared is a quarter, so that becomes a quarter v squared, so half m times a quarter v squared. And let's check this out quickly. Half times 1, 4. Okay, so we just go back to the question quickly. Okay, so that's right. So, okay. Let's see if that multiplies out to 2 there. And that multiplies out to 2 there, that's 2e divided by 4. It's definitely a half v, because I can see now that this quarter here is the answer that I'm looking for, because that becomes now a quarter v squared. You take that and you take that out, you leave the half here, that's a constant part of it, so that's not going to change anything. So that should just be a quarter v. No, sorry, that makes it now a quarter of the original e, because it changes to a quarter of the original e. And the way to do that, we got the quarter, and because we halved v from 1 to half. So in other words, the velocity must be halved in order to get the quarter of the energy. So 1.5 must be option A. So 1.5 therefore must be option A, which is a half v. So you got to half the velocity in order to get a quarter of your energy. That actually makes sense. That makes sense in my mind. Bit of a difficult question, this one, because we had moving at v speed, kinetic energy of E, and now it changes to now a quarter of that, and we needed to figure out what was the speed of the object at the time. Yeah. That makes sense. Yeah, it had to be a half v. Okay. That was a difficult one. I had to use a bit of logic there to understand that one. The frequency of a wave is for 1.6 is defined as lowest point on a wave, time taken for one complete wave. Most of us are busy doing this now. Number of complete waves per second, number of points phase on a wave. Well, I can already see, because I looked at option C there, it must be the number of complete waves per second, because frequency is equal to 1 over t, which is the period. Right, so for 1.6, it's definitely option C. Sorry, 1.6 first. Okay. Let's continue. 1.7, when two wave crests overlap, the increase in amplitude is due to, well, definitely not cancellation. Definitely not two waves in a phase. That's definitely not when they overlap. So it's between C and D. Destructive, taken from the word destroy. So that looks like when something must disappear, be destroyed, so both. But D looks like something's created. So an increase in amplitude means something new has created. So it must be constructive interference. So sorry guys, keep doing this. 1.7 is D. 1.8, almost done. Which one of the following materials is ferromagnetic? In other words, we know the definition for that. It's easily magnetized. Okay. Chromium, I know that. Carbon, no, definitely not calcium. So it must be C, cobalt. Okay, that's a theory question that's probably given to you in your textbook underneath the list of ferromagnetic materials. So that's something you just have to study and remember. All right, 1.9, nice question here. The SI unit for charge is ampere, volt, ohm, or coulomb. Now, ampere, we know, is the full name for amps, which is current, so it can't be A. Volt is for voltage, it can't be B. Ohm is resistance, it can't be C. So we know it must be D, which is coulomb. Right, and 1.10, which is the final question, multiple choice. Right, the maximum done or maximum work done per unit charge by a battery is the current, resistance, terminal potential difference, or EMF. Okay, well, the maximum work done we know is energy, can't be current, can't be resistance. All right, terminal potential difference, we know that is of the circuit, it can't be that. They want to know of the battery, so it can't be terminal potential difference, therefore it's only option A, which is EMF. Okay, we always talk about EMF of the battery, the voltage stored up in a battery, that is the work done by a battery. Okay, and that is multiple choice. Okay, now obviously the multiple choice questions will be different per exam paper, but you answer them the same way. All right, answer them exactly the same way. And that wraps up 2019 paper 1 of November for grade 10. And we've done all the questions, and last week we got through most of them. I know we did them outside of chronological order, but that's all good. So I hope you enjoyed this video, the completion, and hope you took down some notes. Hope you learned a few things, and we'll catch you in the next one.